This is T. Shivapriya, Assistant Professor, Department of Physics, St. Josephs College of Arts and Science for Women, Hosur. Today we are going to discuss about the specific heat capacity of gases and to find CV by Jolys method. Substances differ from one another in the quantity of heat needed to produce a given rise of temperature in a given mass. The heat capacity of a body is defined as the amount of heat required to raise the temperature of the whole body of that body through 1 Kelvin. The unit of heat capacity is Joule per Kelvin. Then the specific heat capacity of any substance is defined as the quantity of heat required to raise the temperature of 1 kg of the substance through 1 Kelvin. Its unit is Joule kg inverse K inverse 1. We know that the gases can be expanded or compressed easily. In that order, the specific heat capacity at constant volume is defined as the amount of heat required to raise the temperature of 1 kg of the gas through 1 Kelvin when its volume is kept constant. Second, the specific heat capacity at constant pressure Cp is defined as the amount of heat required to raise the temperature of 1 kg of the gas through 1 Kelvin when its pressure is kept constant. Cp is always greater than Cv. Why? Because when a gas is heated at constant volume, the pressure will be increased. As the volume is kept constant, no external work done by the gas. On the other hand, if the gas is heated at constant pressure, the volume will be increased. The gas expands against a constant external pressure, and on doing it does some external work done. Therefore, the heat energy supplied to the gas used in two ways: in raising the temperature and in doing some external work as the gas expands. So Cp is always greater than Cv. According to first law of thermodynamics, del Q equal to del E plus del W. For a perfect ideal gas, PV is equal to RT. Then we substitute the value of del Q, del E and del W. Then we cancel the del T in the above equation. Then finally we get the Cp equal to Cv plus R. Then we rearranging the above equation, we finally get R is equal to Cp minus Cv. Then the above equation is known as the Mayer's relation. Here the value of R is 8.31 Joule mole inverse 1 K inverse 1, where R is the universal gas constant. To find constant volume Cv by Jolys differential steam calorimeter. In this apparatus, two hollow metal spheres A and B are exactly similar in volume and mass, suspended inside the steam chamber C. The two spheres are fixed in the pans of a sensitive balance. The spheres are provided with catch waters to collect the water condensed on the spheres. Two umbrella-shaped covers U1 and U2 to prevent any water condensed on the top of the chamber. The two electrically heated coils P1 and P2 are fixed around the suspension wires to prevent water from condensing round the narrow mouths of the steam chamber. Then one of the sphere is filled with the experimental gas. Then other sphere is completely evacuated. By counterpoising, the mass of the gas M filling one of the sphere is found. The initial temperature θ1 of the gas is noted. Now the steam is briskly admitted into the chamber. Condensation takes place. What is meant by condensation? Condensation is nothing but the process, the physical matter of changes from gaseous into the liquid state. The good example of condensation are morning dew on the grass, water droplets on the outer surface of the cold drink bottle, then the foggy car windows. These are the best examples of condensation in our day-to-day life. Then the steam condenses on the sphere containing the gas than the other because the enclosed gas also has to be heated from theta 1 to the temperature theta 2. So the heat gained by the gas is given by mCV into theta 2 minus theta 1. Then the heat lost by the steam is given by m into L. Here L is the specific latent heat of steam. By the principle of method of mixers, equating the above two equation, that is heat gained by the gas equal to heat loss by the steam, mCV into theta 2 minus theta 1 equal to m into L. Now we want to find out the value of constant volume. So rearrange the above equation. CV is equal to mL divided by m into theta 2 minus theta 1. From the above equation, the specific heat capacity of the gas at constant volume is calculated. Then the experiment is repeated with the evacuated sphere filled with the gas and the other sphere will be exhausted. For securing an accurate result, the following corrections must be applied. Number 1. The expansion of the sphere containing the gas due to increase in temperature and pressure. This may be estimated from your knowledge of the expansion coefficient of copper and the initial and the final pressure of the gas in the sphere. Number 2. Correction for the upthrust on the condensed water on the surface of the two spheres. Number 3. Correction for any slight difference between the thermal capacities of two spheres.